We've developed an equation for the chemical potential of each component in an ideal mixture, but not all mixtures are ideal. So what happens if my mixture is not ideal? Let's look again at the case of a 50-50 mixture of A and B. If we have an ideal mixture where the interactions between A molecules and B molecules is about the same as the interaction between AB molecules, then a 50-50 mixture will mean that I have a 50% chance of evaporating an A molecule and a 50% chance of evaporating a B molecule, so that my partial pressure of B is halved from what it was in pure B, and my partial pressure of A is half of what it was above pure A. As a reminder, this leads to Raoult's law, where the partial pressure of the component above the mixture is equal to the vapor pressure above the pure mixture times the mole fraction of that component in solution. Now, if I have stronger interactions between AB molecules than exist between AA or BB molecules, what will happen is that the ability of a B molecule to get into the gas phase is reduced. And so even if I have a 50-50 mixture, I'm going to reduce the vapor pressure of B above the solution by more than 50% because the interactions between B and A are stronger, making it harder to get B into the gas phase. Likewise, if the interactions between B and A are weaker than the interactions between BB molecules, it will be easier to get the B molecules into the gas phase when they're interacting with A. Therefore, the vapor pressure above the solution will be greater than 50% of what it was above pure B. So for stronger interactions, the vapor pressure of the component above the solution is going to be less than the Raoult's law predicted vapor pressure above the solution. However, for weaker interactions, the vapor pressure above the solution will be greater than that predicted by Raoult's law. How much greater or less than the Raoult's law pressure depends on the details of the interactions between particles and can't be predicted in a simple analytical way. However, we can multiply the Raoult's law expression by a fraction that is less than 1 in the case of stronger interactions to make the equality that the pressure above the solution is equal to the Raoult's law pressure times some fraction less than 1. Likewise, we can fix up the case where the interactions are weaker by multiplying our Raoult's law expression by a fraction greater than 1. This fraction, which we give the symbol gamma, is called the activity coefficient. Introducing the activity coefficient allows us to describe all solutions by the same equation. The pressure above the solution is equal to the pressure above the pure solution times gamma sub I, activity coefficient, times the mole fraction of that component in solution. We define the activity coefficient times the mole fraction as equal to the activity of the component in solution. So we can see that for ideal solutions, the activity coefficient is equal to 1, and we recover Raoult's law. When the activity coefficient equals 1, the activity is simply equal to the mole fraction of that component in the solution. When the interactions in the mixture are stronger than the interactions in the pure liquids, the activity coefficient is less than 1, as we discussed. The activity is gamma times x. In solutions where the interactions are weaker in the mixture than they are in the pure substances, the activity coefficient will be greater than 1 in order to give us a pressure that is greater than the Raoult's law pressure. And the activity, again, is gamma times x. If we use this more general expression for the pressure above the solution in our expression for the chemical potential, we can write that the chemical potential of a component in a mixture is equal to the chemical potential of the pure substance plus our correction for not being pure, which is now RT times the natural log of the activity of the component in solution. This, then, is the most general expression for the chemical potential of a component in a mixture.